Welcome back to our unit on covalent bonding. Today is the last day that is going to go along with the PowerPoint, but there will be one more video to kind of review covalence versus ionics with you. So that will be the next one in the series. But for now, let's focus on finishing up. Today's big topic is carbon chemistry. Okay, now, just to kind of put this in perspective, this is also called organic chemistry. Organic chemistry is typically a 1 or 2 semester class at college, usually 1 semester. We're doing it in a day. So that should tell you the depth that we're not really getting with carbon chemistry. I don't really need to get too far in depth with you guys, but I want to give you a good overview so that you sort of know the basics of what's going on. So what this boils down to is that carbon plays a very dominant role in the chemistry of living things. And the biggest reason for that is carbon has bonding stability. If you think about carbon, we've talked about this before, carbon has 4 valence electrons. Those 4 valence electrons mean the chances of it forming an ionic bond are pretty slim. Okay? It's either gain 4 or lose 4. Neither of those is a good option. So instead, what we're going to see is we're going to see covalent bonding with lots of different elements. You'll see a lot of H's, you'll see a lot of O's, all sorts of things will bond with carbon. The other thing that carbon really does a lot of is carbon will make little molecules that will link together to make a whole bunch of structures with repeating subunits. Okay, that was a whole bunch, I know. But what I'm really talking about is you'll have a carbon with some hydrogens attached. And then it'll bond to another carbon with hydrogens. And then another carbon with hydrogens. And then another, and another, and another, and another. And you can have these really long structures, okay, that can absolutely vary. Every now and then, something else is thrown in. Maybe it's not a carbon, maybe it's a nitrogen. But it's kind of like the letters in the alphabet. The order that you put them in is pretty important. Okay, if I give you the letters T, S, I, and H, and ask you to make a word using all 4 of those letters, think about it. Think about it. Okay, so hopefully the word that you just made was this. No? No? Not really? Okay, the word you made was hits, right? No? Okay, then you're a Star Wars fan and you made the word Sith, right? Yeah, if you made any other word, bad. Come back to chemistry land. Okay, but even with that one, which we won't talk about, there are huge differences, okay, between the Sith Lords hitting someone and the word this. The order that these subunits in is huge. So today we are going to talk about 4 types of carbon compounds. Hydrocarbons, small molecules with functional groups, complex polymers, and biological molecules. And we are going to start with our hydrocarbons. Okay? Simple hydrocarbons are made of 2 different elements. And I bet if you think hard enough, you can probably figure it out. Hey, what do you know? They're made of hydrogen and carbon, simply in different amounts. What I'm going to put up here next is a picture, or a chart of the various hydrocarbons. Forgive me for the photo quality. Yes, this is totally a screenshot off of my computer and you're looking at the PowerPoint, but it works. These are the simple hydrocarbons, okay? If there is 1 carbon atom, all right, we use the root word meth, and so the name of it is methane. That's CH4. Okay, that's a carbon with 4 hydrogens attached to it. If there are 2 carbons, okay, so I'm going to do this one down here at the bottom, and it's covered in hydrogens, okay, that 2 carbon chain is called ethane. 3 is propane, 4 is butane, 5 is pentane, 6 is hexane, heptane, octane, nonane, and decane. Okay, so there's a couple different things I want to point out about these. One is there are ones that are known as petrochemicals. Okay, you guys are probably familiar with propane, butane, and octane. And hopefully you're familiar with all of them as fuel. We burn them. Okay, butane is in lighters. Propane, you may have a tank at your house. Octane, you hear about gasoline in cars. So that's one thing to definitely notice. The other thing I want you to notice is this notation right here with structure. Okay, and I'm going to switch slides, but I'll come back. CH4 is pretty easy. I can totally understand CH4. But when I look at the next one, I see CH3, CH3. That's a little bit confusing. It's hard to understand what's going on. So this is CH3, CH3. Because if you look carefully at this molecule, I have a carbon bound to 3 hydrogens right there, and then another carbon bound to 3 hydrogens. So instead of drawing the whole thing out every time, it's notated CH3, that's this part, CH3, that's this part. As you get bigger, it's the same idea. Okay, if we look at propane, propane has got 3 carbons in a row. And again, in this case, everything is single bonded, so it's covered in hydrogens. Remember, we're just talking about hydrocarbons right now. So instead of writing this out every time, we look at the 3 different sections with carbon. And so we would write CH3, because there's 1, 2, 3 hydrogens, and that's connected to CH2, there's 1, 2 hydrogens, and that's connected to CH3. Okay, so this is a pattern you see a lot in this chart. You also see as you get bigger, then rather than writing the whole thing out, they tell you the middle section has 3 of those little CH2 units. Okay, but that's what that notation means. That's something that you're going to see a lot of. The other thing that I want to mention with hydrocarbons is this idea of saturation. If something is saturated, it's soaked, it's full. Okay, so whether or not it's saturated with hydrogens will completely affect its shape and reactivity. In biology, you guys should have learned about saturated and unsaturated fats. Saturated fats are full of hydrogen molecules. Okay, so they are literally holding as many of these hydrogens as they possibly can. All right, so there's all those guys. Let me change him. Okay, this guy right here is saturated. So in a saturated fat, what we see is this very brick-like molecule. Everything is on the straight and narrow. An unsaturated molecule usually has a double bond. So if I put a double bond between these carbons, all of a sudden I can't hold as many hydrogens as I did before. Okay, so if I add a double bond, now I'm pretty limited with my hydrogens. So what that does is shape-wise, it puts kind of a kink in the molecule. So this is what we had talked about as unsaturated fats. These get broken off from your bloodstream fairly easily. They're your good fats. Okay, these are like your lard and your animal fat. They get stuck in your arteries. So that's a chemistry thing. It's based on their shape. And it's based on the fact that the amount of energy you need to maintain double bonds and triple bonds is very, very different. So we kind of break this down in terms of saturation into 3 different things. We have alkanes, alkenes, and alkynes. Okay, an alkane is something that only has single bonds. Okay, so I've got carbon single bonded to carbon, and then of course it's covered in hydrogen. Those are saturated. So if we're looking at this one, we'll go ahead and fill him up. Sorry, I'm a little out of space at the top. This is actually a 2-carbon one, so it is what I call ethane. An alkene has a double bond in it. So this time, I'll have carbon double bonded to carbon. Okay, and I can't hold nearly as many hydrogens. Okay, so because it's a slightly different molecule, okay, it's not ethane anymore. This time we call this one ethene. So the alkenes end in enes. They have double bonds. The third one, you probably see where this is going, is a triple bond. Okay, with a triple bond, it's even less saturated. There's even less hydrogens on there. Okay, so this one would be called ethine. So you need to be able to recognize that this is a single bond, this is a double bond, this is a triple. And the letters A, E, and Y are in alphabetical order. Okay, different numbers of carbons change the beginning. So it can be propane, propene, propine, butane, butene, butine. We just use those prefixes we saw earlier, and we change the ending based on the bonding. All right, so the second type of carbon-based molecule we're going to talk about are those things with functional groups. Now, we did this already in the smell lab, so you're a little bit familiar with functional groups. Basically, they're specific groups of atoms that are responsible for your chemical characteristics or your reactivity of whatever molecule they're attached to. You got to remember there's always a close relationship between structure and function, okay, or structure and properties. Aspirin, vitamins, insulin, believe it or not, they're basically made of the same things, okay, carbon, hydrogen, oxygen. But how they're put together really changes what they do. Okay, taking aspirin is not going to help you if you have a vitamin deficiency, all right? Even though they're made of the same things, it really matters how they're put together. So some of the functional groups that we saw before, all right, we saw that OH group, all right? That's a hydroxyl or an alcohol group. Other ones, you'll see a carbon double bonded to an O. That's a carbonyl. A third one, so there's one, there's two. A third one is called a carboxyl group. You have a carbon double bonded to an O, and then you have an O and an H over here. Sometimes they're separated with that line. Other times you'll see them all together. Another one is called an amino group. Okay, that's when you've got a nitrogen with some hydrogens attached to it. And then every now and then you'll see another one with sulfur. The big point of these functional groups is for you to first of all know that they are totally responsible for the chemical characteristics of a model. And two, if you look at an atom, you need to be able to recognize the functional group on it. Okay, so if I gave you this big long string of carbon, okay, and there's H's and H's and H's and just H's everywhere, okay, and then you look at it and wait a second, there's something different. And the SOL says, hey, where's the functional group? You need to be able to say, it's right there. Okay, so just kind of have a small familiarity with these. All right. Third type of carbon-based molecule we're going to talk about pretty briefly are your complex polymers. Okay, your complex polymers are things that are man-made. Okay, when we talk about polymers, that's usually what we're referring to. But for the record, biological molecules are also complex polymers. Okay, the difference here is how they are made. So we have some that are natural polymers. Poly means many. Okay, so many means you're going to have a huge string of carbons. I'm talking hundreds, maybe thousands of carbons in a row. So the ones that are naturally made, your proteins, okay, your nucleic acids like DNA. Then we have ones that are synthetic, and usually when you hear polymer, that's what people are referring to. The synthetic ones are things like polythene and polystyrene. I know you haven't heard of those, but you've definitely heard of plastic. You've definitely heard of styrofoam. That's what polythene and polystyrene are in. Kevlar. Okay, if you think about bulletproof vests, that is a man-made polymer. Nylon. Okay, not just pantyhose, but now we see it in clothes. That's a man-made polymer. So those are all kind of the different kinds of carbon-based molecules we're going to talk about. The only other thing that I want to add, just a couple of vocabulary words, I want to mention the word isomer to you. Okay? Iso means same. If you ever see iso, it means same. So an isomer, this is pretty cool. It's a molecule with the same chemical formula. Okay, so same chemical formula, but a different structure. Okay, so it's literally got the exact same pieces, but it's totally put together differently. Okay, if you take college chem, you'll learn all about naming these. I'm not worried about you naming them. What I want you to just kind of have a basic understanding of is that this is possible. For example, butene. Okay, butene is going to have 4 carbons in it. So sometimes we see these carbons double bonded to a carbon. I got a hydrogen on this side, another carbon with some hydrogens over here, hydrogen on this side, another carbon over here. That is one kind of butene. But believe it or not, it's possible for it to be put together a different way. Sometimes, okay, the CH3 and the H, okay, will actually be flipped on one side. And believe it or not, these are 2 different molecules. And they can even have slightly different properties. So whether or not, the H's are on one side or the H's are diagonal, That really makes it slightly different. If you write out the formula, it's going to be the same. You've got 1, 2, 3, 4 carbons, okay, no matter where you look, and then you've got 3, 6, 7, 8 hydrogens. Okay, butene is going to be C4H8. But these two things both have that formula. So that's the idea of an isomer. Okay, same formula, same parts, but putting them together differently allows some changes. The other word, and the last word that I want you to know, is the word allotropy. And I'm once again going to import a lovely picture from our PowerPoint. When you look at this one's a horrible image. Sorry, it's a little blurry. I want you to first focus on this picture, okay? This picture right here, this first one, all right, that's a diamond. I'm not sure if you can see that, all right? This is graphite. What are diamonds made of? Carbon. What's graphite made of? Carbon. But clearly, they are very different, okay? If somebody gives you a graphite ring, I don't think you're going to marry them. I think you're going to be a little upset. On the flip side, if a teacher hands you a pencil with a diamond in it, you're probably going to be, well, freaked out and hopefully happy at the same time. That's what allotropy is. It's the property of some elements that allow them to exist in different forms based on how they're put together. So the carbon in diamonds is put together like that. Cool little weird grid. In graphite, it's kind of these more flat sheets that are all piled up. And if you think about a pencil, if you ever looked really close at a pencil, you can appreciate that. This is one of the coolest things going right now. This is something called graphene, and you are actually looking at a picture of it right here. Every one of those dots is a carbon atom. Graphene is a single sheet of carbon atoms. It is flexible, it is crazy lightweight, but it is tough. They are looking at it for body armor. They're looking at it for bulletproof. They're looking for it for all sorts of things. Because even the body armor they have now has still got some weight to it. This stuff is 1 atom thick. You could sew it into your clothes and never know it was there. That's how amazing this is. And that's allotropy. It's the ability of an element, like carbon, to exist in all these different forms, okay, with very different properties. So, you've got a good grasp now on carbon chemistry. Hopefully you've got a good grasp on the rest of covalent bonding. I'll post one more video coming up with this chapter, and it'll be a different night I put it up, but it will help you review ionics and covalents to get ready for your test that covers both.